Okay, in this video we are going to look at the orbitals and how they work to make molecules in the shapes that we previously established by the VSEPR rules. Okay, and this also serves as the introduction to this chapter here, alkanes. Alkanes are what we call hydrocarbons that don't have any single bonds or double bonds in them. And let me just illustrate here how organic chemistry is going to be taught. It's going to be taught using the functional group approach. Okay? A functional group is a small grouping of atoms or a structural feature that leads to a characteristic reactivity pattern. On the book jackets of our textbook and most other textbooks, you'll see a listing of the common organic functional groups. For the next month or the rest of the first half of organic chemistry, we're primarily going to be concerned with hydrocarbon functional groups. And hydrocarbons are molecules that are composed only of carbon and hydrogen. There are basically four hydrocarbon functional groups. The alkanes, which contain only single bonds and no multiple bonds. Alkenes, also known as olefins, would contain a carbon-carbon double bond. Alkynes would contain a triple bond, and aromatics would contain a benzene ring. Okay, amongst all these functional groups, alkanes are by far the least reactive of all hydrocarbon of all other functional groups. Okay, this is the only chapter where there's not really going to be any detailed discussion of a reaction. We're going to look at combustion, but we're primarily going to be looking at the energy released and how that can relate to structure. Okay, alkanes, because of their lack of reactivity, are often just considered as molecules that don't have functional groups. They're referred to as unfunctionalized compounds. Okay, an alkane with no cyclic or ring components has this formula, CnH2n plus 2. And among hydrocarbons, you cannot have any more hydrogens per carbon than in a non-cyclic alkane. Alkanes, for this reason, are also known as saturated hydrocarbons. Okay, they're saturated with hydrogen. You can't possibly cram any more hydrogens into a certain given number of carbons than you can with alkanes. Another synonym for alkanes is paraffins. Okay, let's look at how we can look at the valence orbitals of carbon and hydrogen to arrive at the structures for some of the molecules we looked at in the previous chapter. We're going to focus here on the tetrahedron, exemplified by the simplest organic compound of them all, methane. Okay, so in organic chemistry, we really only have s and p orbitals. S orbitals, shown here, are spherically shaped. Orbital phase can be positive or negative, or we can say shaded or unshaded. And you have to combine like phases for bonding. Okay, so let's look at the basic shapes of orbitals of the p series. Okay, so down here we have p orbitals. There are three p orbitals. They correspond to the Cartesian axes. There's a py, a px, and a pz. It's a little hard to draw the pz. It's hard to draw an orbital with an inward or outward projection. Okay, this is the ground state configuration of a gas phase carbon atom. most of the compounds, or actually all of the compounds, frankly, that we're going to deal with, are going to have carbons not as free atoms, but as part of a structure. Okay, so we can get more bonds if we just take one of these s electrons and move it to the higher p orbital. And this is what we call promoting an electron. Okay, so when we promote the electron, we now have 4 bonding sites, but we see that we still really haven't adequately described what's going on in a tetrahedron here. Okay, because in a tetrahedron, we have bond angles that are 109 degrees. And if we're just looking at hydrogens attached to p orbitals, we realize that this would give us 90-degree bond angles for 3 of the bonds. Okay, so this can't be the whole story right here. So what we do here is one final step where we mix or hybridize the s and p orbitals. So we have sp3 orbitals, and each of these orbitals is 25% s, 75% p. And now, from these orbitals, all of our bond angles are going to be equal. Okay? All of these orbitals are mixtures of, again, 1/4 s and 3/4 p. Okay, let's look at what a hybrid orbital looks like. Okay, so when we combine like and unlike phases, what we're going to do here okay, so we'll shade that side and we'll shade this side. What we're going to find here is that on this side they cancel and this end is going to get smaller, and on this side over here they add and this side is going to get larger. Hence we have the sp hybrid. The x here can be 1, 2, or 3. We usually don't say 1. If it's 1, we just usually call it sp. Okay, the sp hybrids are ideal for making a type of bond known as a sigma bond because they're pointing out to what they're bonding to. Okay, so a sigma bond in organic chemistry consists of a sp hybrid orbital overlapping with an s orbital if it's a hydrogen, or overlapping with another s and p hybrid orbital if it's a carbon-carbon, carbon-oxygen, or carbon-nitrogen. Okay. We can also bond another way using a pure p orbital, and this is the pi bond. Okay. The sigma bond is a direct overlap, whereas the pi bond is a side-on overlap. Okay, the degree of overlap is higher for a sigma bonding, right? And as a result, sigma bonds are generally stronger than pi bonds. Okay, throughout organic chemistry, we can more or less make this relationship here. In organic chemistry, a sigma bond is going to result from an overlap of an sp hybrid orbital, or an s orbital if hydrogen's involved, while the pi bonds in organic chemistry are going to be constructed from p orbitals. That's an important generalization to remember. Okay, so here's methane. It's a little hard to draw orbitals coming in or going out, so what we're going to do is we're just going to show the 2 orbitals that are in the plane of the screen, and we'll assume that the other 2 orbitals would look like it, but they wouldn't be flat on the paper like this. Okay, so it's the methane, the sigma overlap of hydrogen 1s orbitals with carbon sp3 orbitals. That describes every one of the CH bonds. Okay, a slightly more complicated molecule is ethane, C2H6. It also has nothing in it but sigma bonds. But one of the sigma bonds, the CC bond, is formed from two sp3 orbitals at carbon overlapping with each other. This is an important association to remember. The tetrahedral geometry correlates with sp3 hybridization. Okay, we're going to now look at sp2 hybridization and how it associates with trigonal geometry. Let's go back to the most simple of all the trigonal molecules, BH3. This is our ground state boron. We're going to promote it, but we know the job isn't finished because these two p orbitals would be at 90-degree angles, and that does not describe BH3. All the bond angles are 120 degrees. Okay, so we have to go a step further and hybridize. Okay, this p orbital is empty, so it really isn't going to be involved in any sort of bonding, so what we do is we just hybridize the s with the two p orbitals. Okay, so this gives us sp2 orbitals. And these are a little bit, have a little bit more s character than the sp3 orbitals. They have the same general shape. Okay, so each BH bond, like shown here, results from overlapping a sigma orbital of an sp2 orbital at boron, sigma overlap of an sp2 orbital at boron with an s orbital at hydrogen. There's an empty p orbital that got left out of the hybridization scheme. It's important because remember when we were discussing Lewis acids and Lewis bases, we saw how trivalent boron compounds were Lewis acids. So this p orbital is the site of Lewis acidity. Okay, so we're going to look at an organic molecule now, ethylene, or CH2 with a double bond. Okay, because it's now carbon instead of boron, there's an extra electron, and we need a CC sigma bond, so we're going to also use the sp2 hybridization scheme. Okay, notice that each of the carbon atoms has a singly occupied p orbital. Okay, so we can make a second bond just by overlapping the p orbitals, as you see here. And this, of course, is a pi bond. Okay, so that we now have a carbon-carbon double bond. And the carbon-carbon double bond, the two bonds are not equal. There's a sigma bond and there's a pi bond. Okay, as we'll see when we compare energies of some of these compounds, the sigma bond is actually stronger than the pi bond. Okay, and this is true for all other carbon or all other double bonds to carbon. Okay, or at least of the elements we commonly deal with. So a carbon-oxygen and a carbon-nitrogen double bond would also be made as a sigma and pi bond. Okay? Okay, let's look at linear geometry, which we associate with sp hybridization. Okay, so here's a linear. Okay, so we're going to look at acetylene, which has a CC triple bond. Okay, so each carbon atom is going to be attached to two other things. So we only need two sp hybrid orbitals, okay? Alright, this is going to leave two p orbitals out of the hybridization scheme, and remember that these two p orbitals are going to be at 90-degree angles relative to each other. Okay, so the structure that we end up with is two carbons, each with a bonded as a sigma bond, and each of them has two sigma bonds, a sigma bond to hydrogen from an sp orbital at carbon overlapping with H, and a carbon-carbon bond formed by overlap of two sp orbitals. Okay, this leaves two p orbitals available for making pi bonds. There's one pi bond right there. Okay, even though I'm showing like a bond to each lobe, remember that it's only one bond. Okay, and here we also have another pi bond. Okay. Alright, so our triple bond consists of one sigma bond and two pi bonds. And remember, linear geometry is associated with sp hybridization. Okay, let's see how hybridization is affecting bond strength and bond length. We've looked at this before and noticed that as the degree of bonding increases, the bond gets shorter. Here's a single bond, 1.54, a double bond, 1.34, and a triple bond, 1.2. Okay, the CH bond, or let's look at the bond, let's look down here at the bond strength. It gets stronger. But remember, 375 times 2 equals 750. So it's not 2 times as strong. And this reflects the fact that the pi bond is weaker than the sigma bond. Okay, so it's not twice as strong, but it's still much stronger than the single bond, and the triple bond is even stronger still. Okay, let's look at the effect on the CH bonds. Okay, sorry about this thing here. I'm not fully 100% familiar with it. As the S character is increasing, we're getting shorter bonds. So we're seeing a increase in S character at carbon we're seeing a shorter and stronger bond. This is because the s orbital is much closer to the nucleus than the p orbital, and as the percent s increases, the bond gets shorter. Okay, so this is carbon sp3h, and this is carbon SPH. Okay, so not only does it get shorter, it's also getting stronger. Okay, so the bond strength of hydrogen at sp carbon is much stronger than hydrogen at sp3 carbon. Okay, remember bond dissociation energy is defined as delta H for just breaking the bond. All right, so these are important effects for bond strength and hybridization. Okay, let's do a couple of problems here. Again, you should pause the video, do them yourself, and then restart the video when you're ready to verify that you just got the correct answer. What's the structure for allene? Is it A or is it B? Well, it turns out that it's B. Okay, the reason here is because when we look at the central carbon right here, it's linear. It's got two atoms attached to it. Thus, it is sp. And it has two p orbitals at 90-degree angles to each other. Okay, let me put in the dots for the electrons. Sorry about that. All right, so what we see here is that the p orbitals that are parallel engage in a pi bond. Okay, but these pi bonds are coming at 90-degree bond angles to each other, and thus the CH2 groups are also going to be at 90-degree bond angles to each other. Okay, so that because of the sp hybridization and the fact that the pi bonds form at 90-degree bond angles. That means the CH2 groups are also going to be at 90-degree projections at the two N carbons. Okay, here's another question for you. How many pi bonds are present in the following compound? And inherent here is the fact that a triple bond is 1 sigma and 2 pi bonds, and a double bond is 1 sigma and 1 pi bond. Okay, thus there are lots of CH single bonds and CC single bonds in this molecule, but none of them count, or none of them contribute toward the total pi bond count. Okay, so there are 6 pi bonds. Each each carbon-carbon double bond provides 1 pi bond, and each carbon-carbon triple bond is providing 2 pi bonds for a total of 6 pi bonds. Okay, what we've described before is called valence bond theory. A more accurate description of a molecule is had by molecular orbital theory. In valence bond descriptions, we just kind of isolate the orbitals at one particular atom and look at it as kind of an isolated case. But in reality, the whole molecule interacts. And this is where molecular orbital theory comes in. It often gives a more accurate answer than valence bond description. And we're not really going to see cases where we really need molecular orbital theory until chapter 10. So thus, I am going to only go through the very basics of MO theory. Okay, so in molecular orbital theory, we have the atomic orbitals shown here in magenta. These are just the orbitals of the free hydrogen atoms that have not combined to make a bond yet. Okay, in blue we see the molecular orbitals. Okay, right here. All right, so we have atomic orbitals and molecular orbitals. One rule in drawing molecular orbital diagrams is that the number of atomic orbitals has to equal the number of molecular orbitals, 2 and 2. Okay, the general scheme is to put the atomic orbitals on the outside of the diagram and put the molecular orbitals in the middle of the diagram. This energy here, in this diagram, as we go higher up in the diagram, we're increasing in energy. And this energy level right here, which is kind of in the middle, is the energy of the free atoms, and this is known as the energy of non-bonding. Okay, so by combining these, we combine them in 2 ways to get 2 orbitals out of this. We combine the like phases, and this is favorable. This is the bonding orbital. And we can combine the wrong phases, and this is bad. In fact, this is so bad that it's even worse or even higher in energy than if the hydrogens never interacted. Okay, so in the anti-bonding orbital, we're going to combine like phases or unlike phases. Okay, a general term that's ascribed here is HOMO for the highest energy occupied molecular orbital. That's this one, or sigma, because it's a sigma bond. This is the highest energy one that has some electrons in it, and we're going to give the name LUMO to the orbital over here. This is the lowest energy unoccupied molecular orbital. Okay, the net energy, the difference between non-bonding and our HOMO is our net stabilization of our molecule. Okay, here we see how bonding is very favorable as long as we have more orbitals in sigma than in sigma star. We have bonding. This quantity here is called bond order, and I've got this backwards. It's the number of electrons in the bonding minus the number of electrons in the antibonding. Sorry. And thus this is 2 minus 0 over 2. From this diagram, you can also tell an important fundamental thing about atomic structure. Helium-2 does not exist, okay? And why is that? Well, that's because we would have 2 electrons in the atomic orbitals, and thus we would have to occupy the anti-bonding orbitals, and thus there would be no net stabilization. And that's how molecular orbital theory can actually help you here. You can draw a perfectly good bond, but as you can see here, you can't really draw a good bond. Sorry about that. But here you can see how there would be no net stabilization if you had a couple of electrons. This is where I'm going to end the part 1 video. Okay.